Okay, so before we start, I have two quick announcements to make. One is that the midterm date will be October 17th, so that's still still a month away. There's still at least 2 to 3 weeks of like material that we'll cover that will be on the midterm. But I just want to announce it now in case you're trying to sort of make some specific plans or anything like that. And then the lecture before that, I guess, I don't know, we'll probably do some sort of review type thing. Like I'll give you guys a practice midterm or something based off the previous years. And maybe we'll go over it on the lecture before on the Monday or something like that. So that's the first thing. Then the second is that you should have received an email from bspace saying that there were some notes posted. So basically, this is like 15 or 20 page sort of handout that I wrote up that summarizes all the things that we'll be talking about over the next like 3 or 4 lectures or something like that. So this is the first, I think, sort of official reading for the course that you really should, in fact, read in the sense that it'll be important for understanding the studies that we look at later, and that in turn will sort of help you on the exam. So what we're gonna sort of shift now. We've been talking about sort of environmental theory and just economic theory in general for the first few weeks here, and now we're going to shift to talking about basic empirical tools. So if you've already taken econometrics and you understood it really well, then very little of what we say in the next like 3 or 4 lectures is going to be very new to you. But in my experience, like the vast majority of you haven't taken econometrics, and even if you did take it, you might not retain that much of it. So I think that for probably 80 or 90% of the class, this will essentially be new material, even if you've seen some of it in various statistics or econometrics courses. And the goal here is basically trying to give you enough understanding of how the statistical techniques that the papers use, how those techniques actually work, and to give you enough understanding of basically the strengths and the weaknesses of these techniques to be able to form some sort of opinion about whether or not what the paper's concluding is actually credible or not. Okay, so to start out with here, we're going to talk about how one might estimate or think about relationships between variables. So in empirical work, as in life, what matters are relationships. So let's think about 2 variables, which we'll call x and y. And just to make the example more concrete, let's consider a context or a topic that's important in environmental economics. So let's suppose that x represents the daily air pollution levels, and y represents daily hospitalizations. So x and y are the variables, and then you can see that there's an index I that's like a subscript here. So the way that I've set it up right now, you would think of I as basically subscripting the day. So like x1 would be the pollution level on day 1, and x2 would be the pollution level on day 2, and so forth. If you have n observations or n data points in your data set, then that means you have n days worth of data in that data set. But later on, things are going to get a little bit more complicated, and we'll start having maybe multiple subscripts for our variables. So there might be like an I subscript that represents which particular individual we're talking about if we have a data set that consists of like actual surveys or measurements from individuals, from people. And then there might be like a T subscript that would represent like a time period, be it the week or the month or the year or something like that. But for right now, let's just say that I is subscripting days. And so what we're interested in learning is what the relationship is between air pollution and hospitalization. So do hospitalizations go up or do they go down when air pollution rises? And these 2 questions right here are empirical questions. So we have some sort of theory that says that pollution is bad, contaminants in air are bad for people because it impairs lung function or whatever. And so that suggests to us that maybe we would expect for hospitalizations to go up when air pollution rises, but we don't actually know exactly how those mechanisms work in all the cases, and we don't know, just because there's a theoretical mechanism doesn't tell us what the actual magnitude of the relationship is. So it's possible that maybe these pollutants are bad for human health, but the levels at which they're currently present in the air is just too low to actually cause any measurable change in hospitalizations or mortality or anything like that. So figuring out the answers to these questions basically requires data, and they are fundamentally empirical questions. So we want to know if hospitalizations go up when air pollution goes up, but in the real world, very few relationships are deterministic. So to give an example that I'm sure is like near and dear to your heart, if you study for an exam, you probably know that on average you're going to do better, but you don't know exactly how much your score will rise. And in fact, you don't even know if it'll rise at all, right? Like you know that. So if you study a particular topic and then that topic shows up on the exam, then probably you're going to do better than if you hadn't studied that topic. But there's lots of topics in a given course, and maybe you end up studying like some specific subjects or topics or whatever that don't end up showing up on the exam. And so even though in expectation you think that you'll do better by studying, there could be some cases where in fact you just perform the same as if you hadn't studied. So what we're interested in are relationships that hold basically on average or in expectation. So we don't think we know so much about the world that we can say with exact certainty that if we have you study or if we reduce the level of air pollution by 100 grams per however many, or 100 parts per million or whatever, we won't know exactly how much your score improves, or we won't know exactly how much hospitalizations will fall. We'll only be able to say that on average maybe your score will improve by X points, or on average maybe hospitalizations will fall by 3 hospitalizations per day or something like that. So one way to summarize the relationship, let's say between air pollution and hospitalizations, is through what we call the covariance between the 2 variables. So if x and y have a positive covariance, which is say covariance of x and y is greater than 0, then we expect y to be higher when x tends to be high. And if they have a negative covariance, which is say covariance of x and y is less than 0, then we expect y to be lower when x is high. So the covariance tells you the sign of the relationship, but it doesn't actually tell you the exact magnitude of the relationship. And specifically, if your question is how many units is y going to change if I observe that x changes by 1 unit, then the covariance doesn't actually answer that question. And so what we need instead to think about is what we call the conditional expectation of y given x. And this is a function. This is going to be a function of x that basically tells you how much you should expect y to change with a 1 unit change in x. So this term, conditional expectation, has 2 parts. And as you can imagine, the 2 parts are first conditional and then second expectation. And so you need to sort of understand each of these parts well in order to understand what a conditional expectation is. So let's actually tackle the second part first. So the expectation part we'll talk about first before we move on to the conditional part. So the expectation, or sometimes we call it the expected value of a variable, is the average value that you would compute if you could observe that variable a very large number of times. So often we'll think about, or we'll sort of hypothesize a case in which you had an infinitely large sample, and if you could take the mean of the variable of interest across or within an infinitely large sample, then basically that would give you what the expectation of that variable is. So in our example, let's suppose that we have a data set that contains 10,000 days on which we observe daily hospitalizations. So remember, y is the number of daily hospitalizations. And then let's define mu, which is going to be the expected value of y, as being the average number of daily hospitalizations. So just to throw out a random number, it could be the case that mu is equal to 7.6. So what that would say is that when you take the mean of the number of hospitalizations across all days in your data set, you end up calculating a value of 7.6. Did you have a question, Alexis? So if mu is 7.6, let's suppose that we randomly draw 1 day out of our 10,000 days from the data, and then we observe the number of hospitalizations on that day. So we'll draw day I out of the data and observe yi, which is the number of hospitalizations on day I. What you're going to see is that the value of y is going to be some integer, right? So it's going to be like 6 or 10 or 4 or 15. It's not going to be 7.6. So you know with certainty that it's not 7.6 because there's no such thing as like a fractional hospitalization. Either somebody gets admitted to the hospital or they don't. So it has to be an integer number. And it can take on a lot of different values. So even though the mean, if you round it off to the nearest integer, the mean would be 8, you don't expect that on any given day that the number of hospitalizations you observe is always 8. So because of that fact, we call y a random variable because it can realize different values on different days. So some days have more hospitalizations, some days have less hospitalizations. Okay, so now let's suppose that we repeat this experiment thousands and thousands of times. So we could randomly draw a day from the data, and during each of these repetitions, we could expect the average value of y to equal 7.6. So even though on any given day you're never going to observe 7.6 hospitalizations because it can only be an integer number of hospitalizations, when you draw thousands and thousands of days and then you calculate the average number of hospitalizations across those thousands and thousands of days, you would or you could expect it to be equal to 7.6 on average.
So are we defining the 7.6 as like the meal, the two meals?
Yeah, so 10,000 observations, right. So that's a good question. So the way that I'm setting this up, yeah, the answer is yes. You'd want to think of the 7.6 as being the true value of the true expected value, which is the true value of mu here. And then you're drawing a sample from this very large sample. But so I think the reason you're asking the question though is because you could think of that very large sample as itself being some sort of sample of like an entire population, right? So that could potentially be true. If you already like have a good understanding of statistics, then basically you can think of the expected value as being like the population mean of the random variable, and then when you draw a sample from that population and calculate the mean within that sample, then that would be like the sample average. But if you're not sort of familiar with the concepts of the population and then drawing a random sample from that population, then you can just think of the 10,000 day sample as being basically the entire population of this, giving you the true value, the true expected value of the random variable here, and then we're drawing a subsample from that 10,000 day population. I should also note that the way that I'm setting this up, the way that I'm describing it, you can potentially draw the same day twice. So on average, of course, if you draw 1 day and then you go and you draw a second day, or you draw 1 day, put that day back into the sample, and then go perform the experiment again by drawing a second day, it would be very unlikely that you would draw the day that you had just drawn. If you were randomly sampling, there would only be a 1 in 10,000 chance. But in principle, it could happen. And if you were drawing like 5,000 days, then you would probably end up that you draw the same day twice at one point. Okay, so because it's the value that you would expect to get when you compute the average over many of these draws, we call it the expected value. So it's so notationally, what we write is the expectation of yi is equal to mu, which is equal to 7.6. And the thing to emphasize here again is that you never expect to observe yi equals 7.6 for any single day I, because yi only realizes integer value. So just because we call it the expected value doesn't mean that you actually expect to observe that exact value when you draw a single data point from your larger sample or from your population. But the idea is just that if you draw many data points and then take the average over all of those draws, then you expect to get 7.6 on average. Okay, so I want to do sort of a couple of group exercises here, and so the first one is just going to be on expected values, and then the second one, which we'll do, so we'll do that. Then I'll talk for another like 10 or 15 minutes about conditional expectations rather than just raw unconditional expectations, and then we will have you guys meet again and do an exercise related to conditional expectations. So I think the second exercise you'll probably find a little bit more challenging than the first exercise, at least in my experience working with other classes. But right now, so you should be in your groups already. If not, move around so you are. And then there's 3 things I want you guys to calculate the expected values of. So the first one. So the first one is going to basically be the expected value of a coin toss. So you have a fair coin. So the random variable y here is going to equal 1 if a fair coin comes up heads. And then it'll equal 0 if that same coin comes up tails. The second one will be the expected value of a random variable where yi is equal to the number of dots on the face of a 4-sided die. Yeah, so apparently like nobody has ever done was it like Dungeons and Dragons or something like that. We'll get to that in a second. And then so all the coins and dice here are fair. Like they're not biased towards a particular face or a particular side. So the 4-sided die, if you've never seen it, because most dice are 6-sided, and most people have seen those because it's a cube. But the 4-sided die is like a it's not, I don't want to say a pyramid, because a pyramid actually has like 5 sides. But this basically is like a triangular shape that comes up. So it ends up having 4 sides, and then the 4 sides are 1, 2, 3, and 4. So like they have these in role-playing games or something, but I admittedly have not seen one in like 25 years. So calculate the expectation of the number of dots that you would see when you roll the fair 4-sided die, and then in the last one, calculate the expected number of dots you'd see when you roll the 6-sided die. Yeah, so this is 1 to 4, and then this is 1 to 6. Okay, so I'll give you guys like 3 or 4 minutes to do this, and then collect the answers. Yeah.
So look at those three, the value of
Yep. Okay, so I'm just going to randomly pick groups here, or maybe non-randomly. So group number 6, you guys get lucky because you get the first one, which should be the easiest. So what's your answer for this? Okay. You're joking, right? Okay, so that one I think is very straightforward because even if you don't know the exact formula for expectations, you kind of know, well, there's 50-50 chance of each side, so there's a 50 chance I'm going to see 1, and then there's a 50% chance I'll see 0. So half the time I see 1, half the time I see 0, on average it's going to be equal to 1/2 then. Okay, group 7, what is your answer for the four-sided die? 2.5. Yes, that sounds correct. So what's the formula that you use for that? Right. So it'd be equal to like 1 plus 2 plus 3 plus 4 over 4. If you don't have a calculator, one thing that's easy to do is to recognize that 1 plus 4 add up to 5 and 2 plus 3 add up to 5. So like there's a 50% chance that it's either 1 or 4, and the average of those two numbers is 2.5, and there's a 50% chance it's either 2 or 3, and the average of those two numbers is 2.5, and so then the overall average must be 2.5. So if you guys say that in fact the die were unfair and so that you could never roll a 1, but you had an equally weighted chance of any of the other 3, how would the answer change at that point? This is group 7 still. 9 over 4. 2 plus 3 plus 4. Yeah, so that's very close, but I think it's 9 over 3 then. Right? Yeah. Yeah, so you basically knock out this probability, or you knock out this outcome, but then the probability of any of the 3 remaining outcomes is just 1/3. So another, like, to do expected values, basically you take the probability of each outcome and multiply it by the value of that outcome. So implicitly, like I think most people know this at least intuitively, but explicitly what you're writing out here is the probability that yi, actually I better use a different subscript here, say yj, or yi is equal to j times the value, times the value j there. So when you're looking at all 4 sides being equally weighted, then you have 1/4 here, and then you're adding up 1, 2, 3, or 4, depending on which index you are on in the sum here. And when you knock it down to basically having only 3 sides coming up, 2, 3, or 4 equally weighted, then this becomes 1/3, and then you're just summing over 2, 3, and 4 instead of summing over 1, 2, 3, and 4. And then, so group 1, you guys, so your answer to part C is, yeah. So that's the same calculation as the 4-sided die, but now you're just summing over all 6 sides and dividing by 6 instead of dividing by 4. Okay. So I think that's pretty straightforward, but so it's important to understand what an expectation is, but that's not sort of what we're ultimately interested in, right? Because what we're interested in is the relationship between 2 variables, and the expectation is just telling you what value of a particular variable you can sort of like turn around a little bit now if you're facing backwards. So it's telling you what value of what the average value of a variable would be if you observe that variable many, many times. But it doesn't tell you how that variable might change with a second variable. And so to think about how we might measure the relationship between 2 variables, we're going to switch from talking about talking about expectations to talking about conditional expectations. So the idea here is that if we condition our expectation of y on another variable, on the value of another variable x, then potentially our expectation of y is going to change as that variable x changes. So let's suppose that we have this 10,000 day data set, which I said was contained the average number of hospitalizations on each day. But let's suppose that it also contains the second variable x, which is information on the daily number or the daily air pollution levels. So if there's a relationship between x and y, which is say that their covariance is not 0, then we might consider conditioning our expectation of y on the observed value of x. So for example, we might expect y to be somewhat higher on days with higher pollution, and we might expect it to be somewhat lower on days with lower air pollution. So we write, like in terms of notation, what we write is that the conditional expectation of yi given xi is equal to, or is written as, this e of y given xi is equal to little xi. So the idea here is that y and x are both random variables in the sense that, so y is the number of hospitalizations per day, and so that can vary from day to day. X is the air pollution level per day, and that also can